Hello friends, welcome to my lecture on transportation problem. This first lecture on this topic. Let us first see what is the transportation problem. The transportation problem is a special class of linear programming problem that deals with shipping a commodity from a source, that is a factory to a destination which is a warehouse. The objective is to determine the shipping schedule that minimizes the total shipping cost while satisfying supply and demand limits. The general problem is represented by the network as shown in figure 1 here, this figure. Okay. So, there are m sources and n destinations. You can see there are m sources, okay, 1, 2 and so on up to n m. There are m sources and n destinations, 1, 2 and so on up to n. Each represented by a node. Each source and destinations are represented by a node. Now, the arcs represent the routes linking the sources and the destinations. So, these arcs, okay, these arcs between sources and destinations, okay, represent the routes that link the sources and the destinations. Arc I j joining the source I to destination j carries two pieces of information. Okay. So, if you consider the node I and the destination j, okay, node I and the destination j, then the arc I j, okay, the arc I j which joins the source I to the destination j, it carries two pieces of information: the transportation cost per unit, okay, which is denoted by C I j, and the amount shipped, that is X I j. The amount of supply at source I is A I and the amount of demand at destination j is B j. Okay. So, here at the source I, okay, the amount that is available is A I, and at the destination j the demand is given by B j. Okay. So, amount of supply at source I is A I and the amount of demand at destination j is B j. The objective of the model is to determine the unknown quantity X I j that will minimize the total transportation cost while satisfying all the supply and demand restrictions. So, X I j is the amount that is shipped from ith location to jth destination, from the ith source to the jth destination. So, the X I j's are unknowns. We have to determine the values of X I j, that is the amount that is to be shipped from the ith source to the jth destination, okay, for each I and j. Now, so this is the network, okay, that represents this transportation problem. Now, we let us consider its mathematical formulation. So, let there be m origins and n destinations. Now, n may or may not be equal to m, number of sources may not be equal to number of destinations. Now, ith origin, okay, possessing A I units of a certain product and jth destination requiring B j units of the same product. Okay. So, there are m origins and n destinations, n may not be equal to m, okay, and at the ith origin there are A I units available, and at the jth destination we require B j units of the same product. Okay. Let us assume that total quantity of product available is what? At the ith location we have A I units available. Okay. So, and I is equal to 1 to m, okay, because there are m sources. So, total quantity available is sigma I equal to 1 to m A I. This is total quantity available. And at the jth destination we require B j units of the same product. J is from 1 to n because there are n destinations. So, total quantity that is required is the, sigma j equal to 1 to n B j. So, this is total quantity required. So, let us assume that total quantity that is available to us for shipment is equal to total quantity that is required to us. Okay. So, sigma I equal to 1 to m A I equal to sigma j equal to 1 to n B j. Let C I j be the cost of transportation of 1 unit product from ith origin to jth destination, okay, and x I j be the quantity transported from the ith origin to the jth destination. Then the problem is to determine non-negative values of x I j satisfying the availability restrictions as well as the requirement restrictions in such a way that total transportation cost is minimized. So, that is our problem. Now, that means we have to find x I j's, okay, unknowns x I j's, non-negative values of x I j's for I equal to 1 2 and so on up to m, j equal to 1 2 and so on up to n, which minimize the total cost. Total cost is sigma I equal to 1 to m, sigma j equal to 1 to n, C I j into x I j. C I j is the cost per unit of transporting from ith source to jth location, okay, and x I j is the quantity that is shipped from ith location to jth destination. So, C I j into x I j is the cost incurred in transporting x I j units from ith source to jth destination, and I runs from 1 to m, j goes from 1 to n. So, when we take the summation we get the total cost, and sigma j equal to 1 to n, sigma j equal to 1 to n means now A I is the quantity available at the ith source. From ith source the quantity is being transported, okay, to the n locations, okay, where that means j equal to 1 to n destinations. So, the total sum of x I j, okay, j equal to 1 to n should be equal to A I, because at the ith source we have A I units available with us, okay. So, those A I units are transported to the jth n destinations. So, the total of x I j, I mean for j equal to 1 to n, okay, for the ith source will be equal to A I, and sigma I equal to 1 to m x I j equal to B j. At the jth destination we require B j units of the product, okay. So, that B j is units of the product are being made available, okay, by the m sources, okay. So, sigma of x I j I equal to 1 to m, okay. Now, some of the x I j's may be 0, there may not be any shipment from some sources, okay, and there may be some from which positive x I j value will be there, okay. So, x I j's here for some i's could be even 0, that means from those sources there is no shipment of the product, okay, to the jth location. So, sigma I equal to 1 to m x I j is equal to B j. So, these are the constants, okay, on x I j. Now, the equations 3 and 4, these equations 3 and 4 are called as row and column equations respectively. Now, the objective function 2 and the constant equation 3 and 4 are all linear in x I j. You can see here this, okay, they are all x I, they are linear in x I j, okay. So, it is a linear programming problem, it is a special type of linear programming problem, and since all x I j's are greater than or equal to 0, okay, since all x I j's are greater than or equal to 0, A I is greater than or equal to 0 and B j is greater than or equal to 0 for every j I and j, okay. So, each A I is greater than or equal to 0, each B j is greater than or equal to 0. Now, let us see what is a feasible solution. A feasible solution to a transportation problem is a set of non-negative individual allocations x I j greater than or equal to 0, which satisfies the row and column sum restrictions, that is sigma x I j I equal to 1 to m is equal to B j, sigma x I j j equal to 1 to n is equal to A I. So, a set of non-negative values of x I j, okay, which satisfy the row and column sum restrictions is called a feasible solution to the transportation problem. Now, a necessary and sufficient condition for the existence of a feasible solution of a m by n transportation problem is sigma I equal to 1 to m A I equal to sigma j equal to 1 to n B j, okay. So, we have the transportation problem here, it is m by n transportation problem, because you can see here I runs from 1 to m, j runs from 1 to n, there are total m plus n equations here, okay. these are m equations, these are n equations, this is m by n transportation problem. It will have a feasible solution if and only if sigma I equal to 1 to m a I, sigma I equal to 1 to m a I equal to sigma j equal to 1 to n b j. So, this condition is necessary and sufficient for the existence of a feasible solution to a transportation problem. So, this condition we have assumed, and therefore, our problem will have a feasible solution. Now, a transportation problem in which this condition sigma I equal to 1 to m a I, sigma j equal to sigma j equal to 1 to n b j holds true is called a balanced transportation problem. Okay. So, we are considering the transportation problem as balanced, because we have assumed that sigma a I is equal to sigma b j, where I runs from 1 to m, j runs from 1 to m. So, hence from the above theorem we can say that a balanced transportation problem always has a unique solution. Okay. So, in the transportation problem, if total quantity of product available is equal to total quantity of product that is required, then such a transportation problem is called balanced transportation problem, and it will always have a feasible solution, that is guaranteed by this theorem 1. Okay. Now, a feasible solution to a transportation problem is said to be basic feasible solution if it contains at the most m plus n minus 1 strict positive allocations. Okay. So, there are m plus n equations, right. There are m plus n equations, total variables are m n. Okay. X I j's, I runs from 1 to m, j runs from 1 to n. So, total variables are m into n. Okay. A transportation problem will be said to have a basic feasible solution if it contains at the most m plus n minus 1 strictly positive allocations, otherwise the solution will degenerate. If the total number of positive allocations is exactly m plus n minus 1, then the basic feasible solution is said to be non-degenerate. See, now out of m plus n equations, there are m plus n equations here, you can see there are m equations here, n equations here. So, total of m plus n equations involving m n variables. Okay. So, there are out of m plus n equations, in a m by n transportation problem, one equation is redundant and remaining m plus n minus 1 equations are linearly independent set. So, let us show that this follows from here. So, let us take m equal to 3, for example, let us take m equal to 3 and n equal to 4. Okay. So, then when m is equal to 3 and n equal to 4, let us see, we will have these equations. I is taking value from 1 to 3. Okay. So, I is taking value from 1 to 3. So, I equal to 1. I equal to 1 will give you x 1 1 plus x 1 2, x 1 3, x 1 4 equal to a 1. Okay. Then I equal to 2. I equal to 2 will give you x 2 1, x 2 2, x 2 3, x 2 4 equal to a 2. I is equal to 3 will give you x 3 1, x 3 2, x 3 3, x 3 4 equal to a 3. Okay. So, these are 3 equations as a result of this one, and there will be 4 equations as a result of j equal to 1 2 3 4. Okay. So, j equal to 1. So, we will get x 1 1, x 2 1, x 3 1. Okay. I is taking values from 1 to 3. So, x 1 1, x 2 1, x 3 1 equal to b 1. Okay. There will be 4 equations as a result of this one. Okay. Then j equal to 2. So, we will get x 1 2 for j equal to 2, x 1 2, x 2 2, x 3 2 equal to b 2, and then x j equal to 3 will give you x 1 3, x 2 3, x 3 3 equal to b 3, and x j equal to 4. So, x 1 4, x 2 4, x 3 4 equal to B4. Okay. Now, let us consider A1 plus A2 plus A3 minus B1 plus B2 plus B3. Okay. See what we will get. Okay. So, A1 plus A2 plus A3, we are adding this one and this one and subtracting B1, B2, B3. Okay. So, what we will get? So, x11 plus x12 plus x13 plus x14, okay, that is A1, plus x21, x22, x23, x24 and then x31, x32, x33, x34. So, these are first three equations give us this. Okay. Then minus x11 minus x21 minus x31 minus x12 minus x22 minus x32 and minus x13 minus x23 minus x33. Okay. So, A1 plus A2 plus A3 minus B1 minus B2 minus B3. Okay. So, x11 cancels with this one, x11, x21 cancels with x21, x31 cancels with x31, x12 with x12, x22 with x22, x32 with x32 here. Okay. x13 with x13, x23 with x23, x33 with x33. Okay. So, we get x14 plus x24 plus x34. Okay. Now, we have been given that the transportation problem is balanced. So, sigma A I is equal to 1 to 3 equal to sigma B j equal to 1 to 4. Okay. That is A1 plus A2 plus A3 equal to B1 plus B2 plus B3 plus B4. This is given to us. Okay. So, A1 plus A2 plus A3, this is equal to B1 plus B2 plus B3 plus B4 minus B1 minus B2 minus B3 equal to x14 plus x24 plus x34. Okay. So, we get, yeah. So, this gives us x14 plus x24 plus x34 equal to B4, which is this equation, 7th equation. Okay. So, out of these 7 equations, one equation, this equation can be obtained from the other 6 equations. So, this equation is redundant. Okay. So, out of the m plus n equations, any one equation is redundant and remaining 6 equations are independent. They form a linearly independent set. Okay. So, that is the verification for this theorem. Okay. Now, from this above theorem, it follows that a basic feasible solution of an m by n transportation problem will contain at most m plus n minus 1 positive variables, while the remaining m n minus m plus n minus 1 variables will be 0. So, taking m plus n minus 1 taking m n minus m plus n minus 1 variable 0, okay, the remaining m plus n minus 1 variables, okay, can be determined from the m plus n minus 1 variables. So, that is why it says that there will be at the most m plus n minus 1 positive variables, while the remaining m n minus m plus n minus 1 variables will be 0. So, a basic feasible solution can be obtained, okay, from these m plus n minus 1 equations. Now, a feasible solution, not necessarily basic feasible solution, is called optimal if it minimizes the total transportation cost. Okay. So, feasible solution will be called optimal if it minimizes the total transportation costs. Now, let us determine a basic feasible solution. Okay. So, the solution of a transportation problem consists of following 2 steps. First, we find an initial basic feasible solution, okay, and then we will find an optimal solution by making successive improvements to initial basic feasible solution, okay, that is obtained in the step 1. until no further decrease in the transportation cost is possible. So, let us first go to step 1 and try to determine an initial basic feasible solution. Then we shall find an optimal solution corresponding to the step 2. Now, using the step 2. Now, there are 3 methods which we use to find an initial basic feasible solution. The northwest corner rule, that is one method, the other method is least cost method, and the third method is Bogle approximation method. So, let us first discuss method 1, northwest corner rule. In this rule we have the following steps. Okay. So, we form the transportation table in the cell 1 1. Okay. Let us see what kind of table we will have. This kind of table we will have here F1, F2, F3, F4 they are sources. Okay. W1, W2, W3 are the destinations. Okay. So, destinations are written here, sources are written here, okay. And these are transportation cost, okay, per unit from source F1 to destination W1. The transportation cost per unit is per unit of the product is 2, from the source F1 to the destination W2 it is 7, from the source F1 to the destination W3 it is 4, and so on. Okay. So, these values 274, 331, 547, 162 they are the transportation costs from the sources to the destinations, and these values 5, 8, 7, okay, 14 they are the units available at the source F1, F2, F3, F4. Okay. So, 5 units of the product are available for shipment at the source F1, 8 units are available at the source F2 for shipment, 7 are available at the source F3 for shipment, and 14 are available at F4 for shipment. Now, what are the requirements of the 3 sources W1, W2, W3? The sources means warehouses. At the warehouse W1 the requirement of 7 units of the product is there, at the warehouse W2 9 units of the product are required, and at the warehouse W3 18 units of the product is required. Okay. Now, we have assumed that so these are the values, this is A1, A2, A3, A4, okay, the quantity that is available, okay, at the sources F1, F2, F3, F4, and these 7, 9, 18 they are the values of B1, B2, B3. Okay. Now, we have assumed that sigma AI I equal to 1 to m is equal to sigma Bj j equal to 1 to n. So, here we have right. So, I equal to, so A1 plus A2 plus A3 plus A4, let us see how much is that. So, total quantity that is available is 5 plus 8 plus 7 plus 14. So, that is equal to 13 plus 7 20 plus 34. Okay. And what is the quantity that is required at the 3 warehouses? B1 plus B2 plus B3, that is equal to 7 plus 9 plus 18. Okay. So, this is also 34. Okay. So, the quantity that is available for shipment is 34, the quantity that is required for at the 3 warehouses is also 34. So, it is a balanced transportation problem, okay, and therefore, we can find initial basic feasible solution. Okay. Now, these are cells, okay, this is 1 1 position, this 1 1 2 position, this 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, 4 1, 4 2, 4 3. Okay. So, at the ijth entry means this is ijth entry, the entry in the 3rd row 2nd column. Okay. It tells us the transportation cost. Okay. This is Cij. Okay. The transportation cost from ith source to jth location. So, let me say for the particular value of I and j, So, I could say that C32 is equal to 4. The transportation cost from the source F3 to the location W2 per unit is 4. Okay, right. So, now in the cell let's see what is northwest corner rule. Okay, northwest corner rule. So, start with the cell 1 1. Okay, this is cell 1 1. This is 1 1 cell. Okay. So, start with the cell 1 1. Okay. What we will do that, and you can see this 1 1 cell is also the northwest corner. Okay. So, this is northwest corner of the table, and the topmost left corner and the so the northwest corner is the topmost left corner. You can see this is topmost of this table, this is the topmost left corner. Okay. So, what we will do here, allocate their maximum possible amount. Okay. To the topmost left corner, allocate their maximum possible amount. Now, how much maximum possible amount we can allocate, that we have to see. See, Xij is the quantity that is to be allocated. Okay. So, here x11, x11 what should be the value of x11? X11 should be equal to minimum of A1 B1. Why it should be minimum of A1 B1? You see, this is A1, okay, and this is B1. At the warehouse W1 we need 7 units of the product, okay, but here at the source F1 only 5 units are available, 5 units of product are available for a shipment. Okay. So, we can at the most allocate 5 units to the cell W to the cell 1 1, okay, the top left corner. To the top left corner we can at the most allocate 5. So, that is why we say, okay, if the requirement is of the maximum allocation could be only 5, okay, 5 7, minimum of 5 and 7 is 5. So, we will allocate 5 to the topmost left corner of this transportation table. Okay. So, x11 will be equal to minimum of A1 B1, okay. Minimum of A1 and B1 should be allocated to the topmost left corner of the table in this northwest corner rule. Okay. So, x11 is minimum of A1 and B1. So, we will allocate 5 to this column, okay, to this cell. Now, then if B1 is less than A1, let us go to step 2. If B1 is less than A1, then if B1 is less than A1, then minimum of A1 B1 will be B1. Okay. So, x11 will be equal to B1, and there is still some quantity left. Now, let us see here, it is B1 is greater than A1, you can see in this problem B1 is greater than A1. Okay. B1 is greater than A1. So, if B1 is less than A1, then some quantity will be available in left row, left in the row 1. Why? Because here if this A1 is more, okay, it is 5 here, but if it A1 suppose was 8, okay, and here it was 7, then minimum of 7 and 8 would have been 7. So, we would have allocated 7 here only, okay, in the cell 1 1, okay, and then there out of 8 units, 7 units we have allocated to the cell 1 1, we would still have 1 unit to allocate. Okay. So, if B1 is less than A1, then some quantity will be left for allocation in the first row, okay, and therefore, there will be some quantity left in the row 1. So, move to the right hand cell 1 2, then we will move to the right hand cell 1 2. Okay. So, suppose it is here it was 8, it was 7 here, 7 be allocated here, 1 unit will be left, then to allocate that 1 unit we will move to the cell W2. In the cell W2, okay, we need at the warehouse W2 we need 9 units, okay, and we still have 1 unit which can be allocated. So, that 1 unit we will allocate to cell 1 2, okay, and so on. So, what we will do here, there is still some quantity available in left in row 1. So, move to the right hand cell 1 2 and make the second allocation of amount. Now, how much will be that amount? x12 will be left over, okay, A1 minus x11. Okay. We have allocated B1, the leftover is A1 minus x A1 minus B1, that is A1 minus x11. So, A1 minus x11 and B2, that minimum of that we have to take, and that is to be allocated to cell 1 2. Okay. Now, in case B1 is greater than A1, like in our problem, here you can see this B1 is 7, A1 is 5. Okay. So, what we will have? We have allocated 5 here, still 2 units are needed for the warehouse W1. Okay. So, we move down to the cell 2 1, okay, and in the cell 2 1, okay, we have we can allocate 2 units which are left over here, okay. Because we needed 7, we have allocated 5 here, 2 more are required, those 2 can be given to the cell 2 1, okay. Requirement is 8, okay, and at the location F2 we have at the location F2, at the source F2 we have 8 units available. So, from 8 we will give 2, take 2 and give to this cell 2 1, okay. So, that total availability of W1, total quantity available at the warehouse W1 is exhausted, okay. We get 4 5 here from the source F1 and 2 here from the source F2. So, if V1 is greater than 1 A1, then x11 will be equal to A1, and there is still some requirement left in the column 1, okay. So, move vertically downwards to the cell 2 1 and make the second allocation of amount x21 equal to minimum of A2, and this should be A2, minimum of A2 and minimum of A2 we have to take, okay, minimum of A2 and B1 minus A1, okay, because A1 we have already allocated. So, from B1 we will subtract A1, okay. So, B1 minus A1 and A2, okay, this should be A2. So, minimum of A2 and B1 minus x11, that will be allocated to 2 1, cell 2 1, okay. Now, if B1 equal to A1, suppose this quantity A1 is equal to B1 here, okay, then what we will do? We will allocate this value here, and then we do not have to go this we do not have to allocate further to in the first row or in the first column. So, we can omit first row or we can omit first column, because we have already allocated the amount that is required to the warehouse W1, okay, and the amount that is available in the source 1, that is also exhausted. So, we will cross out the first row or we will cross out the first column, we will not cross out both. So, if B1 equal to A1, then x12 or x2 equal to 1 equal to 0. So, start from the new northwest corner of the transportation table and allocate there as much as possible, okay. So, suppose we have crossed out the first row, then we will have this table, second row, third row, fourth row. So, this is our new table. So, we will again consider the northwest corner of this table, that is the 2 1 cell will now be the new northwest corner of the table, and we will repeat these steps. So, repeat steps 1 and 2 until all the available quantity is exhausted or all the requirement is satisfied. So, let us see how we do this here, okay. So, you can see here this is our northwest corner, okay, northwest corner. We at the source F1 quantity available is 5, and at the warehouse W1 we need the 7 quantity 7 units of the product, okay. So, we take minimum of 5 and 7, allocate 5 to this cell W1, okay. So, 5 is allocated here, okay. Now, so 5 we will cross out here, 5 will cross out here, and now there is nothing more which can be allocated from the source F1. So, we cross out the first row, okay. Now, here 5 has already been allocated. So, it will become now 2, okay. 2 units more are to be allocated. So, we move vertically down, okay, come to this one, okay. Now, here we are at the source F2 we have 8 units available, Okay. So, we can allocate 2 out of 8 to this to one cell. Okay. So, that this becomes 0 here, and here 8 minus 2, it becomes 6 here. Okay. Now, we have allocated all we have the requirement of the first warehouse W1 is fulfilled. Okay. So, we cross out the first column. Okay. And now, what is left with us? This table is left with us, this table. Okay. This is left with us. So, northwest corner is this one. Okay. Northwest corner is this one. Now, we take the minimum of 6 and 9. Okay. So, minimum of 6 and 9 is 6. So, we allocate 6 to this column, this cell. Okay. So, 6 is allocated here, okay, to this cell. So, this becomes 0, and here we get 9 minus 6. So, we get 3. Okay. Now, from the warehouse F2, we have allocated all the 8 units. Okay. So, we cross out this row. Okay. And now, what is left is this table, this one 4 7, okay, 6 2. So, this is left with us. Now, the northwest corner is 4, okay, this corner 3 2, this northwest corner. So, here what is the availability at F3 is 7, okay, and we have 3 more units are needed at the warehouse W2. So, 3 and 7, the minimum is 3. Okay. So, we allocate 3 here, okay, to this. Okay. So, then this column is now crossed out, because we have allocated we have the W2 has been allocated all the 9 units. So, 3 we subtract from here, and we get 4. 4 are still to be allocated. Now, from the source F3, we are to allocate 4, at 4 units are available at F3, okay, and we have at W1 and W2 have been allocated, only W3 remains to be allocated. So, from F3, W3 will now receive 4, okay. So, this will receive 4, okay, these ones, and from F4 this one will receive 14, okay, the 4 3 cell, okay. F3 will from F3, okay, W3 will receive the remaining 4, okay, and from F4, okay, W3 will receive this 14. So, what we have? So, the allocations are to the cell 1 1 we have allocated 5 units, to the cell 2 1 we have allocated 2 units, to the cell 2 2 we have allocated 6, to the cell 3 2 we have allocated 3, and to the cell 3 3 we have allocated 4, to the cell 4 2 no 4 2 no not 4 2, to the cell 4 3 we have allocated 14. Okay. So, how many allocations are there? 1 2 3 okay, 4 5 6 allocations are there, where the all 5 units, okay, from F1 are allocated to the warehouse W1. Out of 8 units available at the source F2, 2 have been allocated to the warehouse W1, 6 have been allocated to the warehouse W2. From the source F3, 3 units have been allocated to the warehouse W2, and 4 have been allocated to the warehouse W3, and from F4 all the 14 units have been allocated to the warehouse W3, and the total transportation cost is now you can see 2 into 5, okay, then we have 3 into 2, and then we have 3 into 6, and then we have 4 into 3, then we have 7 into 4, and then we have 2 into 14. Okay, so, how much is that? 10, 6, then we have 18, then we have 12 here, then we have 28 and then we have 28. Okay, so which is 102. Okay. So, this is equal to 102. So, the total transportation cost is 102 rupees. Okay. This is the total transportation cost, and this is the new table. From F1 we have allocated all 5 quantities to the cell 11, to the cell 21. From F2 we allocate 2, and to the cell to the warehouse W2 we allocate 6. From F3 we allocate 3 to the warehouse W2, 4 to the warehouse W3, and from F4 all the 14 to the warehouse W3. Okay. So, that is the total transportation cost. So, this is northwest corner rule. Now, let us go to the next method, which is least cost method. In this method we have following steps: examine the cost matrix carefully and find the lowest cost. Okay. Let us say it is Cij, then allocate Xij as much as possible in the cell Ij. Okay. So, Xij is equal to minimum of Ai and Bj. Okay. So, we will inspect the whole cost matrix, okay, and whichever cell has got the lowest cost, to that cell we shall allocate maximum possible value, that is maximum possible will be minimum of Ai and Bj. Okay. That, so, because Ai is the amount available at the ith source and Bj is the amount required at the jth destination. So, minimum of Aij, that much is the maximum value which we can allocate. So, minimum of Aij will be Xij, that will be allocated to the ijth cell. Okay. Now, if Xij equal to Ai, suppose Ai is less than Bj. Okay. So, if Xij equal to Ai, then the capacity of the ith origin, okay, is completely exhausted, because Ai is the quantity that is available at the ith source. So, ith origin is completely exhausted. In this case, cross out the ith row of the transportation table and decrease the requirement of Bj by Ai. So, Bj will be reduced by Ai. Now, we will go to step 3. So, what is step 3? Repeat steps 1 and 2 for the. So, after that we will repeat steps 1 and 2, okay, until all the available exhausted and all the requirement is satisfied. Now, else what we will do, if Xij equal to Bj, okay, if Xij is not equal to Ai, but Bj, that is Bj is less than Ai, then the requirement of jth destination is completely exhausted, okay, completely satisfied. So, in this case, cross out the jth column, we will cross out the jth column of the transportation table and decrease Ai by Bj, and then we will go to step 3. Now, if Xij equal to Ai or Bj, then either cross out the ith row or jth column, but not both, and go to step 3. So, step 3 is this where we will repeat steps 1 and 2. Now, if the cell of least cost, okay, is not unique, suppose there are more than one cell, okay, where the cost is given to be least. I mean, it is not a unique cell, that is just one cell where the least cost is there, more than one cells are there where the least cost is given, okay, then we can select any of these cells to begin. Okay. Now, let us see, we again have the same example which we have taken in the case of northwest corner. So, let us apply the least cost rule here. Okay. Now, we see the cost matrix. So, we have 2, 7, 4, 3, 3, 1, 5, 4, 7, 1, 6, 2. They are the cost of transporting a unit from one source to another warehouse. Okay. From F1 to W1 it is 2 per unit, from F1 to W2 it is 7 per unit, from F1 to W3 it is 4 per unit, and so on. Okay. So, let us see minimum, I mean the least value among all these values is 1, 2, 7, 4, 3, 3, 1, 5, 4, 7, 1, 6, 2. So, 1 is the least among all these values, and 1 occurs at 2 places, here as well as here. We can select any one cell to begin. Okay. So, let us say suppose I choose this cell, okay, that is the cell where we have second row and third column. So, this is 2 3, cell 2 3. Okay. In the cell 2 3 the cost is 1 rupee for transporting a unit of product from the source F2 to the warehouse W3. We could have also considered this cell which is cell 4 1, fourth row and first column. Okay. Suppose I have selected this one, then to this cell we will allocate the maximum quantity, and maximum quantity will be the minimum of the quantity available at the source F2 and the quantity required at the warehouse W3. Okay. So, at the warehouse W3 we require 18 units. So, we take minimum of 8 and 18. Okay. So, minimum of 8 and 18, that is equal to 8. So, we allocate 8 here. Okay. We allocate 8 here. So, after we have allocated the 8 units, okay, the availability of F2 at F2 we had 8 units available. So, that is exhausted. So, okay, so we will cross out this row. Okay, we will cross out this row, and after that now what is the table available with us? 274, 547, 162. At 8 have gone already been allotted allocated to W3. So, it will become 10 now. Okay. Now, 274, 547, 162. So, we again find the cell which has got the least cost. So, this cell has got the least cost now. Okay. So, we will allocate minimum of xi ai bj. Okay. Now, here what is we have 14 units are available at source F2, 7 are required, okay, at W1. So, minimum of 7 and 14 is equal to 7. So, we allocate 7 here to this. Okay. So, we have allocated 7. So, now the requirement of the availability at F4 is reduced to 7 units are remaining to be allocated, and here W1 has got all the 7 units that are needed. So, what we will do, so this will cross this column, okay, this column, because the requirement of W1 is satisfied. Okay. So, we will cross out this column. Now, what is left with us? 7 4, okay, 4 7 and 6 2. Okay. So, which is minimum? 7 4, 4 7, 6 2. Least cost is 2. Okay. Least cost is 2, and what is the minimum of now we have to take minimum of 7 and 10. Okay. Minimum of 7 and 10 we have to take. So, minimum of 7 and 10 is 7. So, we allocate 7 here. Okay. We allocate 7 here. So, 7 has gone now. Okay. So, we cross out this row, okay, and this will remain now 3 more are to be made available to W3. Okay. So, now, what is left with us? So, we have 7 4 4 7. Okay. So, minimum is 4. Okay. Now, we can take either this 4 or we can take this 4. So, let us take this 4 for example. Okay. We take this 4. So, we then consider minimum of 5 and 3. Okay. So, minimum of 5 and 3, that is equal to 3. So, we allocate 3 here. Okay. So, we now left with 2 here, okay, and here this 3 has gone. So, we will cross out this column, we will cross out this column. Okay. Now, so we have here now okay, so 2, this 2 can now F1, from F1 W2 can be given this 2, okay, and then from F3 this 7 can be given to W2, okay, and then when we gave 2 to W2 from F1, this 9 became 7, and then we gave 7 from this F3 to W2, it became 0. Okay. So, what we have done from F1, 2 units are given to W2 and 3 units are given to W3. From F2 we are giving all 8 units to W3. From F3 we are giving all 7 units to W2. From F4 we are given 7 units to W1 and 7 units to W3. Okay. So, what is the transportation cost? this is equal to 7 into 2, okay, then 4 into 3, okay, then we have 1 into 8, and then we have 4 into 7, then we have 7 into 1 into 7, and then we have 2 into 7. So, this is 14 plus 12 plus 8 plus 28 plus 7 plus 14. Okay. This is 83. So, we get transportation cost to be rupees 83. So, by applying this least cost method, the transportation cost comes out to be rupees 83, while in the case of the first method, that is northwest corner rule, we got the transportation cost to be 102. So, this method is better because here we take into consideration the least cost of the cost matrix and allocate maximum of quantity that is available, that is we say Xij is taken as minimum of Ai and Bj, and that is allocated minimum of Aij and Bj, that is Xij is allocated to the cell Ij, where the least cost Cij occurs. So, that is why it gives us a better result than the northwest corner rule. So, this is the matrix where you can see from F1 we have allocated 2 to the we have allocated 2 to second cell. Okay. So, these are allocations, okay, these are allocations. In the brackets we are writing the cost per unit, while the values that are written without bracket, they are the allocations, the Xij's. Okay. These are this is x12, this is x13, this is x23, and this is x32. Okay. So, and this is x41, x43. Okay. So, they are these values 2, 3, 8, 7, 7, 7. Okay. They are the allocations to the warehouses from the sources F1, F2, F3, F4. Okay. So, these 5 units that were available at F1, okay, out of that 5, 2 have been given to W2, 3 have been given to W3. Out of 8 available at F2, all 8 have been given to W3. Out of 7, all 7 have been given to W2. Out of 14, 7 have been given to W1, and remaining 7 have been given to W3, and the total cost of transportation is 83. So, this is the least cost method. In the next lecture, we shall discuss the Vogel approximation method, which one you will see is still better than these two. So, we will find the transportation cost there, and then we shall discuss the how to determine an optimal solution of the transportation problem. So, with that I would like to end this lecture. Thank you very much for your attention.